Hi, and welcome to this week's Graphics Programming Weekly. This week we're covering Chapter 4, which is of VK Guide, which is double buffering and descriptor sets. I will forewarn you that I'm not going to be implementing stuff this chapter. I leave that as an exercise to the reader because I view this chapter as more important to focus on the whys rather than the hows. And I invite anyone in this call to ask questions freely and interrupt because there's a lot of little nuances and things that happen with descriptor sets that are tricky. So to get double buffering out of the way, I'll quickly go over it. Right now we have a frame setup where we do some work on the CPU, we submit the work, we wait on that work to finish, and then we start on the next frame after that if first frame is done. This is inefficient because the CPU can be doing stuff while the GPU is doing stuff. To make that possible, we pretty much just duplicate all of our resources, specifically semaphores, fences, command buffers, command pool. And so we throw all that in a struct, and then we create an array of that struct. And then whenever we want to render frame X, we use a function to get frame X's data. And if we want to render frame X plus 1, we just increment the, where is the variable? You store the current frame number. Yeah, frame number. You store the current frame number, and then you just modulo it over the number of frames you want in flight. Generally, 2 is just fine. You could go 3 if you want to be crazy, but that's going to be triplicating all the resources instead of just duplicating. So you go through all of this, and the big change is that everything that used to be just a variable access now is frames at I. Yes, comment mentions missing pictures. I literally had a tab open because, and I'll post a link to it in chat for posterity. This is API List Out Secrets, Practical Approach to Vulkan Part 1, and it's the only part, as it turns out, because the author never continued it. But this image is what we're currently doing. We're doing some CPU work, we're submitting, it's executing on the GPU, and we're waiting on the CPU before starting the next frame. What we want is this, where the CPU is making frames while the GPU is working. And this is what we get when we have multiple command buffers, fences, semaphores, and all that. Oh, the white on white is hard to read, but you can see that this is our current frame structure, and we want the blue and red to be overlapping, not one after another. So there's a lot that there's a lot of nuances and fun, tricky corner cases you can get into. If you start queuing up like 5 frames on the CPU, but the GPU hasn't even finished 1, that can get into tricky territory. Generally, you don't let that happen if you're wise about things. Waiting on the n-1 frame to finish before you start frame n+1. So frame n is currently executing, meaning the CPU doesn't start frame n+2 until frame n-1 or n+1 has finished. So you have a fence wait here that makes sure that it, ping pongs back and forth correctly. That's one way to do it. But there's a lot more to be said about it, and if you want to investigate it, you can. We're just going to move on to descriptor sets, which is the big thing. In Vulkan, if you want shaders to access data that are not in vertex buffers, they must go through a descriptor set. A descriptor set is a set of descriptors, which is unhelpfully undescriptive. In Vulkan, you have images and buffers, VK image, VK buffer. These represent the data that a shader wants to use. So textures would be an image, model matrix might be stored in a buffer. But to get that data into a shader, you need a descriptor. Descriptor, in loose words, is a pointer. A descriptor holds the address of GPU memory to a texture, a buffer. And what Vulkan asks us to do is to organize all of the shader resources we want and group them into sets such that each set is a group of descriptors. They don't have to be of the same kind, but they do have to be bound together. You cannot bind a descriptor in its lonesome. You have to bind a descriptor set. Someone need to mute, maybe? I don't know. So if you think of a descriptor as a pointer, then a descriptor set could be thought as a struct of pointers. When you want to render something with a specific group of shader resources, you bind a specific descriptor set, or possibly more than one descriptor set. So you can bind multiple sets at the same time. So in a conceptual model, you can think of whenever you bind a descriptor set, what the GPU is doing is it's writing in a section of memory local to the shaders that are about to run the addresses of all the resources it needs. So if you think of a texture as some memory in VRAM and a descriptor as a pointer to it, when the shader starts running, the GPU has to first write into local memory of the shader core that, hey, this texture you're going to be using, use this pointer to look it up and find and access the data. Because I kept saying that a descriptor is a pointer. Well, pointers take up space and need to be allocated. They're not transient, so you have to create the space for the descriptors to live ahead of time. And so we have an object called a descriptor pool, which owns the memory that the descriptors live in. It's very opaque, so the descriptor pool manages the memory for you. All you're doing is just saying, hey, I want to allocate some descriptor sets from this descriptor pool. And when you create the pool, you have to specify the size of the pool. The descriptors are typed. So a descriptor for an image or a uniform buffer or a shader storage buffer object, SSBO, or a Texel buffer, or an acceleration structure. Don't quote me on that. I've not looked into the ray tracing stuff and how they do their resource stuff management. All of these types of descriptors can possibly have different sizes, and they are definitely differently typed. When you create a descriptor pool, you have to specify how much of each descriptor type the pool could contain. One strategy to combat this is to simply say, hey, I'm going to make a pool with a lot of space for everything. And on desktop hardware, that tends to be mostly okay because there's lots of space for them, VRAM and whatnot. SSBO, shader storage buffer object, yes, that's what commenter asked. When you are allocating descriptor sets, keep in mind that if you can avoid individually freeing descriptors sets, then that may make the driver better able to allocate and reuse the memory. So the optional bit descriptor pool create free descriptor set allows for destroying individual descriptor sets from a descriptor pool. Using it, I'm not positive it's a good or bad thing, but it is a thing that you can choose and opt into. Alternatively, you can just free the pool and free every allocated descriptor set in it all at once. Now that I've kind of introduced the words I'm going to be using, we can see we have a descriptor pool and we allocate descriptor sets from it. Before we can create a pool or a set, we first need to create the layout. I mentioned that descriptors are typed. This layout stores the type and count of the descriptors in a set. And this is used, this descriptor set layout object is used in the creation of the pipeline. When you create a Vulkan pipeline, you have to specify what descriptor sets are going to be used in it because it corresponds to what shaders, what the shaders are going to be using. Side note, it's very convenient to reflect on the shaders binary at runtime to generate the descriptor set layouts, because then you don't have to manually type it out in code and make sure it matches against the shader. They must match up. If they don't, you'll get validation errors and weird behavior. So a descriptor set layout contains the types and the sizes of things. When you allocate a descriptor pool, you'll want to make sure that it has enough space in it for the different types and counts you need. When you create a descriptor set, what it's doing is allocating memory. You don't have a pool. No. When you allocate a descriptor set, it is empty at the start. To fill it, we use VK write descriptor sets. This is effectively writing in pointers into the memory on the GPU. We're assigning the actual resources we want to use. That means a descriptor set is a mutable object. When you create, or when you allocate, I should say, the descriptor set, it's empty. You say you have a material with 3 textures, you know, a rock texture, a sand, and a grass or something. You have this descriptor set and you write in the textures into them. You generate the descriptors when you are assigning, or you're writing that when you're writing the images into them. And we can see that these are pointers and they have byte offsets and images and other things. So a descriptor set is a collection of assets, how they need to be allocated, and their pointers. A descriptor set is a table of pointers to resources. In this situation, I prefer the word resources instead of assets, but assets and resources are definitionally similar enough that you could use either. The descriptor pool is what manages the actual allocation. You allocate it from the descriptor pool, but you're the one who is in charge of writing into that descriptor set the things you want to be in there. We can go down here and see writing descriptors. Is there a code for that? Right, descriptor set. So we have this struct here is the actual write descriptor set. It also includes the binding and the set ID that we're using. We have our descriptor count and type, and then we have a pointer to the buffers or the data we want. If we had multiple of them, we'd have, I believe, multiple elements here. For textures, it's more or less the same. You just have a P texture info. Oh yeah, here's the buffer info. The descriptor itself It's a weird thing to call a descriptor just a pointer because it's not just a pointer. It has much more information about that. We have the buffer handle, but also the offset and the range. How big is it and where in the buffer it starts. So you can have descriptors that are sub allocations of a VK buffer and not the entire thing. That's why there's VK buffer views and VK image views, because that's a useful thing. Yeah, pointer and metadata, yes. There's a similar struct VK descriptor image info that you fill out if you want a image descriptor. The weird thought that I had to come to grips with is a descriptor set is an object you create directly. A descriptor is just a mental concept we apply to the thing that we give information about. This descriptor buffer info is as much the descriptor as is, this is what the descriptor is, but the internal representation will be whatever the driver wants it to be because it's the driver. When we do the update descriptor sets, the descriptor gets created using this source information and information about where in the descriptor set it is. An important note I haven't detailed is that you can have multiple descriptor sets and you can bind them multiple descriptor sets at the same time. The idea is you group your shader resources by update frequency. That way you can bind global data in one descriptor set, per material data in a second descriptor set, and per object data in a third descriptor set. At the start of the frame, you bind the global data and it applies to every draw call you're going to do. Then for every, you start drawing all of the same material. So you draw all the meshes using material X. You'll bind the material data for material X. Then you issue a bunch of draw calls using that material data. And that'd be like your second descriptor. The third descriptor set would be the per object, so your model matrix. So you'll have a descriptor set that's just the objects data, say skinned mesh, all the weights and the current animation pose. So the way it's organized, I'll make this a little bigger, is in the shader code. This is vertex layout location. This is your vertex binding. For shader resources that are accessed through descriptor sets, we have set, comma, binding, and these are the indices that they'll be in. The set is the descriptor set the binding corresponds to, and then the binding number here is the individual index in that binding. So here we have one descriptor set at set location 0 and this camera buffer is binding 0. If we wanted to have a texture in the same descriptor set, we'd have layout set equals 0, comma, binding equals 1, end paren, sampler 2D, and that'd be how we get our another binding in there, and we'll see more instances of that later. So writing, where was the write? Did we write it up above? I believe so. So yeah, this is just going over. So in the code, you have to, we create some buffers for the cameras. We have to create a buffer object for the size. You know, we'll have a struct, and it, you know, the struct needs to match up in the shader, which this thing here, this struct must match this bindings layout. So there's lots of fiddly details with descriptor sets that I hope to mostly ignore in this discussion because they get into a situation where what you need to do depends on what you want to do, and what you do with a descriptor set or how you arrange the descriptor sets depends on what you're trying to do. Are there any questions yet about what I've discussed so far that I haven't already answered? Oh, binding. That's the one thing I hadn't thought about. We bind a descriptor set like we bind a pipeline or a vertex buffer. Because you can bind multiple descriptor sets, it matters which index you bind the descriptor into. That was not very clear. If you had, yeah.
No, like finish what you're gonna say.
If you had 3 descriptor sets you want bound, I'm pretty sure you could bind them in any order. You could bind the third, then the second, then the first, even though conceptually you try to organize them as a stack-like model where you only bind the highest most descriptor sets, because to make use of the multiple descriptor sets bound by their update frequency, the organization of the pipelines is needing to reflect that. If you had a pipeline per material, you'll want the pipelines to share the same base descriptor set layout. So say the global data structure, the globally accessible shader resources, say your frame count, the current time, frame specific stuff like how big is the frame buffer. That stuff you'll want to put in frame descriptor set 0, and every material pipeline or every pipeline will have the same descriptor set layouts at slot 0. Slot 1 could be the material data, and that would vary per pipeline because each material might need a different thing. So your shiny metal material would need a different descriptor set layout than your opaque solid color one. When you bind a pipeline, if the descriptor set layouts are incompatible, then the descriptor sets that are incompatible are invalidated, and you must bind descriptor sets that match it. There is a funky relationship model between descriptors, descriptor sets, descriptor set layouts, pipeline layouts. I did not mention them yet. I should, and I will do this in a second. And render pass, not render passes. There's a very obnoxious relationship between all of these objects. One quick thing: a pipeline layout is a collection of descriptor set layouts. We've already covered them in the pipeline chapter. I remember now, but they didn't do much for us. Now that we have all these descriptor sets to organize, the pipeline layout is just the specific set of descriptor sets we want for a specific pipeline. And that is helpful. So this image, I didn't want to introduce yet at the start, but is a relatively decent summary of this mess that is descriptor sets. Vulkan has many to many relationships. So N to M, name to, or the 2 adjacent letters of the English alphabet, meaning that you can have, that there are many things that descriptor sets do, which do not require one object to one object relations. This is, I'm having a hard time putting into words what that means. This stems from the concept of descriptor set compatibility, or probably better known as pipeline layout compatibility. When you create a descriptor set layout, it describes a layout. The actual object you create does not matter when it comes to the compatibility between pipelines and descriptor sets. They just need to be compatible. It's kind of a vague concept, but if you think of descriptor set layouts as just a description of the layout and not an object that owns, data of sorts, it becomes more clear that a descriptor set layout matching other descriptor sets layouts, even if it's not the same object, makes sense. Like, I want to pull up the VK spec on this. Pipeline layout compatibility, pipeline layout compatibility. Yeah, this guy. There's a whole bunch of rules that you go through, and it mostly is if the things below descriptor set n are match, then everything below that is compatible. And if n and n+1 don't match, then they don't, but it's still everything below it's the same. And it's just obnoxious and complicated. But it stems from the fact that the object handles for a descriptor set layout or a pipeline layout they're not objects, they're just layouts. They just happen to be stored in an object for convenience. So that's a fun consequence. I actually want to look up descriptor types because that's a good list. In a bindless environment, someone asks what happens. The gist is you go from having 25 different descriptor sets organized into different update frequencies where you'll have one global, some per material, some per object. And instead, you put everything into one descriptor set that contains all of your shader resources. In a sense, going back to everything is accessible and individually bound. The difference in a bindless environment is that everything is bound at once by the CPU and accessed through indices either generated or sent to the GPU per invocation. So like you'll have a push constant index into your giant array of buffers and textures. So a good mental introduction to a bindless setup as an approaching bindless is to have all of the textures you have in your scene stored in a single array of textures, and your materials do not store descriptors to textures. They instead just store the index into that array. So all the material buffer is a struct containing 16 or 32-bit indices. And then you can have your descriptor set that's the per material and a descriptor set that is all of the textures all at once. There's lots of good resources on bindless setups, so I'm not going to get too far into that. What I was going to go over was the different types of descriptor types. What was your question?
Yeah.
Or are you?
I eat peanut butter.
But it's candy.
There's no peanuts in
You mute?
this.
That
Like the
smells
mic
good.
is hot.
Yeah.
It's
Yeah.
hot.
We mute that, Leslie. Forcibly? I can't do that because I'm not a host.
Do M&Ms have peanuts?
Okay, so I'm just going to talk over them while someone else deals with that. Thank you.
Yeah, I'm muted.
Thank you. There's multiple descriptor types. There's storage images, there's sampler images. Sampled images is a combination. Isn't that the combination of an image and a sampler? And it kind of has to, oh, that's the combined image sampler right below it. So those are the four main image related stuff. A sampler is just a sampler and doesn't have any texture data associated with it. A combined image sampler is where you combine the image and sampler into a single descriptor. This is more to do with OpenGL compatibility. Other APIs have them as completely separate. It's kind of a whatever for me. Where things get fun is the different buffer layout descriptor types. We have uniform Texel buffer, which instead of it just being a byte array, lets you address a byte array using a specific format that you specify. So you could interpret it as a Texel or an image buffer, but it's format conversion. It's more niche use. A storage Texel buffer versus a uniform Texel buffer kind of has to do with the read-write versus read nature. Oh yeah, uniform buffer and storage buffer, or storage buffer is your SSBO, and uniform buffer is your uniform buffer. The limitation of a uniform buffer is that you can only bind 65,000 bytes at a time, whereas a storage buffer can have effectively infinite amount bound at a time and can be read and written to by a shader. A uniform buffer is a read-only resource type, where a storage buffer is your read-write. If you're doing compute shader stuff, you'll almost invariably reach for the storage buffer because you need to put your output data somewhere from your compute pass. The dynamic uniform buffer is a weird hybrid of a uniform buffer and a storage buffer, because a dynamic uniform buffer is a way to circumvent the 65K limit. The dynamic part of a uniform buffer is that you can set where in the buffer it is bound right before the draw call. I didn't know there was dynamic storage buffer. I guess that makes sense. Really? When was this added? Apparently a long time ago, because there's no ext on it. Dynamic storage buffer and dynamic uniform buffer, they have some associated cost with them, which is necessary to allow their dynamicity. In a strict uniform buffer setup, when you bind the uniform buffer, you're binding it at whatever offset the descriptor write used. So when you did VK update descriptor sets, you specified an offset, and that's whatever the offset uniform buffer will use. The dynamic uniform buffer, on the other hand, lets you specify that offset at command buffer writing time, which is a later time. Inline uniform blocks are funky. They're supposed to be inline, so they might be written into the shader, into the command buffer. I'm not actually very familiar with what their pros and cons are. There's so many ways to do the same thing in the Vulkan descriptor land that it's very hard to know what the right answer is. I mean, we have push constants, but then there's inline uniform blocks, which apparently do very similar things. But my take on why it gets complicated is that Vulkan is supposed to be a low-level API. The API designers had 5 or 6 different hardware platforms, hardware vendors that they're trying to abstract. So they realized they needed a higher level API to manage the descriptor model on all these different vendors, which notably includes desktop and mobile hardware, which have rather different architectures. They needed a somewhat high-level API. The consequence was they also needed a fast mechanism for certain applications. Certain types of data gets updated frequently, some data doesn't get updated frequently. So that's why we have push constants versus descriptor sets. The idea is you update the descriptor set at the start of the application, but and then you leave it alone and just bind it when necessary, versus a push constant where you set the value every frame. There's all sorts of other things that go along with this when you start looking at the various new types of descriptors. And there's push descriptor, which let me find push descriptor, which doesn't descriptor. It's in an extension that's not supported everywhere on all hardware, but it lets you record updates to descriptor sets in a command buffer rather than as a separate function call. One thing that was not well described in my description is that updating descriptor sets using this call is copying the data to the GPU for you. So this function actually does a whole lot of stuff behind the scenes to make it all work. So a push descriptor inverts that a bit and makes the updating happen in the command buffer submission sequence. So you write the data you want, not into a descriptor set that write descriptor set struct that gets updated, that then updates the descriptor set immediately. It happens when you submit the command buffer, because this gets written into a CPU buffer first. Something I didn't note, but I will do it so now, is the fact that whenever you write a descriptor set, you're doing memory allocation. Whenever you bind that descriptor set, it gets marked as in use. You cannot update a descriptor set that is in use. It's undefined what happens. So if you, and this is kind of wacky from the when you're just starting learning about it, because command buffer recording, just conceptually, it just writes data to a CPU buffer. When you do VK command, where does it have it? Bind. Yeah, I'll go to the code that binds it. Come on, where is it? Oh, that's update. That's not it. Where is the bind? Oh yeah, whenever you do this function, it binds the descriptor set and writes into the CPU command buffer, the buffer on the CPU memory, that you're going to use this descriptor set. Once you've issued this function call, you are no longer allowed to update the contents of the descriptor set. Even though in my mind, I'm thinking, well, it's not in use yet. I haven't submitted the command buffer. All I've done is record it. Well, this is to allow driver stuff to happen. And I'm not quite sure why that restriction exists, but it does, and we have to abide by it. Unless you use the flag I was trying to allude to that lets you update after bind. This flag is something that was introduced with the descriptor indexing extension that is now part of core, and it says, hey, I want to be able to update the descriptor set after I have bound it in a command buffer. I'm actually, why is there so many tabs for this extension? Weird. Vulkan descriptor indexing. There's a great YouTube video. Yeah, this one. This is like when the extension was first announced and discussed. You can go watch it and find out more about descriptor indexing. Descriptor indexing relax a whole bunch of the restrictions descriptor sets had. Another flag that it was added that is not discussed, at least in this page, is partially bound. So I'm going to do partially bound and see if I can find it. Yeah. Blah, blah. Partially bound. It's not coming up. Okay, so I wish it was coming up, but I don't know where it'd be in the spec. When you issue a draw call, one of the things the Vulkan 1.0 spec required was that all of the descriptor sets and the descriptors in those descriptor sets have a binding in them, some actual thing in the data. I'm just going to do descriptor indexing. Yeah, this will link it to me. Yes, this is what I wanted to search. Yeah, thank you. Thank you, search thing. Is that it? Oh, I need this. This is a relaxation upon the requirements of the application to fill every descriptor with something useful. And as long as your shader does not access the descriptor, it can have nothing in it. So if you had a descriptor set which contained 4 images and you only use the first 2 images in a shader, OG Vulkan required that the 3rd and 4th image be pointing to an image. With a partially bound bit, it means you don't actually need images in that descriptor set. This is most relevant for when you have a giant array of images or buffers, or a big array that may not be fully used. You may allocate a 10 or 100,000 element array and then only have the first a couple of 100 elements filled out of it. Without this bit, I'm pretty sure you'd pretty much have to do everything. This whole section is actually really helpful to read through if you want to know more about descriptor indexing, because all of these things matter for that. But they start getting out of hand for what I want to discuss. I think I got through everything I wanted to discuss. I'm trying to think if I've missed anything. Are there any questions? There's this great, recently published, like only this 2 weeks ago, T. Wine has been putting out a series on Vulkan, and their descriptors and resources it's a wonderful introduction to the concept. It's not going to walk you through the code like VK Guide does, but a 27-minute introduction to all the things I just discussed, and probably more accurately and in more detail. Where was that image I liked?
I've got a question.
Yes.
And maybe, in fact, almost certainly, I'm sure that the answer is it depends, and it's going to be hardware dependent, workload dependent. But in general, in your experience and your knowledge, is there a big win to be had by making sure that uniforms that are going to not change throughout many draw calls? Like if I'm going to throw over some camera matrices to my shaders, is there a big win by making sure that I'm binding a descriptor set that just has the camera matrices and then binding descriptor sets for each individual material? Or because that's certainly more complex on the CPU side. So is it okay to forego that complexity and just duplicate the camera matrices in every descriptor set for every material? Do you get the question?
Yeah, the question in my words is, if you just had a single descriptor set that is per draw call effectively, that other than if you were using push constants, if you just said, okay, well, I could have descriptor sets separated by update frequency, But what if I just made one descriptor set for every time I need to update anything? But I'm not going to change it at all. So it's, you know, it's a low frequency update thing. I say that the depends answer is yes, it's definitely going to depend.
Yeah, of course.
A thought though is that the cost that is generally associated with not separating by update frequency comes from the cost of updating the descriptor set.
Oh, it's not the bind.
The bind is, if you're rebinding stuff all the time, that can get, you know, slow, but that may not be the only source of performance to think about. Whenever you create a descriptor set, not allocate, but write stuff into it, you're going to have to be transferring data to the GPU. If you're doing that once at startup and then just never doing it again, the descriptor set is, well, the same, and it just uses the same internal table of pointers, that is the internal memory representation of the descriptor set, and just reuses those. And to counter what you're describing, it sounds like you really just want a bindless setup.
I really do.
And your question kind of goes into, if you implement what at least what I'm thinking, you end up with a bindless setup with an obvious, the setup is so ready for bindless that it'd be silly not to turn it into a bindless setup. Where you just have a single descriptor set of everything, or very few descriptor sets that contain many, many things, and you index into them appropriately.
Okay. That makes
Actually,
sense.
let me Meister. Let me blog. Yeah. This series, I thought this was just going to be DXIL, spurvy, nitty-gritty details about bytecode and whatnot. This article is, at least this third one in the series, it might be worth reading the second one. Very enlightening as to what's happening underneath all of these APIs. This is written from a DirectX 12 to Vulkan implementers perspective, but he also talks about DirectX 11's shader model, which is you have slots for everything, and you got registers you can fill up. And it talks about some of the things that DirectX 12's shading model does, which is very different. There's a whole lot of similar terminology, but the way DirectX 12 does their thing is much more manual. Vulkan says, hey, we have this high-level API and to address that we're dealing with a whole bunch of different hardware, and each vendor is going to have to make it efficient for their own thing. But DirectX 12 is a lot more direct for desktop hardware, from my understanding. It maps to the AMD architecture very directly, and there's little of this this diagram. This diagram is not a thing in DirectX 12 because everything's a much more explicit and more like you're given a couple of base objects that interact together in complex ways, but the objects themselves aren't complex, if that makes sense. That probably does.
Yeah, it does.
But DirectX 12, I definitely think if you want to understand descriptor sets, go and try to understand DirectX 12's shader binding model. The difference in perspective makes it a lot easier to grok what's going on, because this feels very abstract. I came from OpenGL. OpenGL is just kind of like, yeah, there's some places you can put some stuff. You query the address of it, but you can also just do it by name if you'd rather, which is very, very slow. Don't do that. Oh, I hope Jerk's that diagram. Did I not share a link to the which diagram are you talking about? I'm just gonna reopen these. Oh yeah, okay. Here's the diagrams and here's the actual image. You can spend quite a while looking over this. I didn't want to go too deep into it because I'd get distracted looking at the beautiful lines and seeing how everything interconnects. Yeah, there's memory stuff you got to think about when you're looking at the buffers and images, but I didn't touch on that much. This is written pre-descriptor indexing. So yeah, I linked this talk, I think.
So to just clarify, I guess, let me just pull up the diagram again. Between the difference between the descriptor sets and push constants. So you would use a push constant for something that is updating like frequently, right? You would use, a storage buffer, a uniform buffer for stuff that doesn't update as frequently.
So that's the annoying thing. I think it's this one. Just quickly say, this is a good article on the craziness of DirectX 12's descriptor model, or that. It's crazy. Vulkan is crazier in my opinion, but it's still crazy because there's a whole lot of stuff that gets thrown at you, especially if you're unfamiliar with all the terminology. To answer your question, when people say update, they do not specify whether they mean updating the values or the descriptors. If I have a model matrix, I am updating the value every frame. The thing's going to be moving and rotating and translating and scaling possibly every frame. I need to update those values, but that doesn't mean I'm updating the descriptor. That uniform buffer, I'm going to be changing the values of, but every frame I'm reusing that same bit of GPU memory. A nice thing about the double buffering is that we'll double buffer all of the uniform buffers. So on frame N, we'll update frame N's uniform buffer. But when I say update, I mean changing the values of. If we look at this guy, we can go to here, map memory, where we map the memory, copy the data in, and then unmap it. What we're doing here is we're changing the values in the buffer. We're not changing the descriptors where the descriptor is pointing in GPU memory. So in this case, you want a uniform buffer, even though you are changing the data every frame. Push constants are a limited resource. There's only 128 bytes guaranteed on all platforms. So you'll want to reserve it for things that you don't want to store a VK buffer and have to access directly. I kept talking about descriptors as pointers. The cost of a descriptor is that it's a pointer and you have to chase the pointer to get the value. If you store all of the indices of your texture, say you're in a bindless setup and you wanted to store all of the indices that a material's textures use, so your albedo, your normal, your roughness, all of those things are just an indice into the texture array. Well, if you store all of those indices in a uniform buffer, you first have to get the descriptor of the uniform buffer, dereference that, look up the values inside that GPU bit of GPU memory, then load those indices, then look up the texture array descriptor, which is another pointer, and each of those indices are going to be indexing into those. And so there can be quite a few levels of indirection that aren't obviously happening with your descriptors. And that's why this article is really nice about it, because it starts getting into some of the indexing. Like here we have this sample plus C push plus C plus C2, and it starts breaking down, you know, what's happening. You're doing all the sorts of addressing of buffers and offsets and things. So that's one of the reasons why it gets so complicated, is that on some hardware, certain things get fit right into the local memory of the shader, whereas other things have to live on the heap, and you have to be mindful of the cost of addressing those, or you know, chasing pointers. Just like you don't want a whole bunch of pointer dereferences in CPU memory or CPU programming. GPU programming has a similar thing. It's just more complicated in practice. So I hope that answered your question.
Yeah, thank you.
Any other questions, concerns, complaints you want to make the world know about? Well, if there aren't any, I think we're done with this for today. And I want to thank you for listening in. That we can move on to the rest of the meeting.